In the last video, we looked at Niels Bohr's model of the atom, and we talked about how Niels Bohr's model decided to take in Max Planck's discovery of the idea that energy was quantized. And so Niels Bohr produced a model that indicated that electrons had to travel in specified or fixed orbits. The problem was with that, although it helped explain and make sense of a lot of things, is it still didn't answer the question of why are electrons traveling in fixed orbits? We know that would solve the problem, but we still don't know why they have to be in fixed orbits. And so the de Broglie equation ends up addressing that issue. So Louis de Broglie looked at previous experiments, the light experiment with Young's double slit experiment, and postulated if light, which was traditionally believed to be a wave, can behave like a particle, could it be true then that particles, such as electrons, traditionally believed to be just a piece of matter, could behave like a wave? And the answer is yes, and that was actually the reason why electrons travel in specified orbits. Let's take a look at an example. If an electron behaves like a standing wave, then it can only have a specific wavelength. For example, in this first picture, imagine this is the nucleus right here, and the electron is moving in its fixed path around the nucleus. Now, Niels Bohr believed the fixed path was this circle that's indicated by the dashed line. But de Broglie postulates that no, the electron is not moving in a perfectly clean circle. Instead, the electron is actually moving in a wave as it goes around the nucleus. But the thing is, the orbit had to be just the right size so that when the electron went all the way around, it would meet up where it started and complete the wave function, meaning it would be able to continue going through and through and through. If the orbit was a little bit smaller, then what would end up happening is the electron would go around in a wave and it would not complete the wave. The wave function would not continue. This area would end up creating the electron to go off of its orbit and either fly off into space or go into and collide with the nucleus. And so this idea that it had to travel in a fixed path was deduced because it was discovered that electrons are actually traveling in waves. So if we take a look at that implication further and further out, this is the nucleus, and this is where we get our energy levels. These are the allowed distances from the nucleus so that the waves will actually end up completing each other. This information right here goes into depth as far as what those distances are. We don't need to know that. Just notice the picture here. If you notice, the nucleus would be like right here in the center of this picture. You could see that surrounding the nucleus are these allowed orbits, but they're allowed because of the wave function. It would end up completing perfectly and would continue, the electron would continue its path going around. So de Broglie was able to prove why electrons travel in fixed orbits. It's not that they were traveling in perfect circles, they were actually traveling like waves. From this, de Broglie came up with an equation. He was able to figure out that we can actually calculate what is the wavelength for any piece of matter, as long as we know the matter's mass, as well as what's the velocity. Notice this is actually velocity, this is not frequency. And so velocity is in units of meters per second. The SI unit for mass is the kilogram. Most of the time we're going to be looking at an electron. So reminder, an electron's mass is 9.11 times 10 to the negative 31st kilogram. If the problem we're looking at is looking at another subatomic particle's mass, such as maybe proton or neutron, reminder that those masses are on the back of your periodic table. And then lastly, you should be familiar with Planck's constant. If we plug in all of this information, we can actually calculate what the wavelength is for any moving particle, whether it's a tiny electron all the way up to a person or even larger still. Now, the thing is, at the macroscopic level, our wavelength is so tiny that it's negligible. We don't even notice it. So we don't really think about humans traveling like waves because it's so small compared to our mass. But when we talk about really, really tiny things, we need to take into consideration that tiny particles such as electrons and protons not only have particle-like properties, but also waves. So let's look at an example where we have to calculate the wavelength of a moving particle. What would be the de Broglie wavelength of an electron that travels at 75% the speed of light, and reminder, has the mass of 9.11 times 10 to the negative 31st kilogram? So we're calculating the de Broglie wavelength, and so remember that's going to be Planck's constant divided by the product of mass times velocity. And I'm writing this a little different because I want you to understand that when you plug this in your calculator, you have to make sure you put this bottom part in parentheses. Otherwise, the calculator is going to calculate the numbers in the wrong order and you'll get the wrong answer. So make sure that you do this math first before you divide it into Planck's constant. All right, so let's plug in our information. We know Planck's constant is 6.626 times 10 to the negative 34th joule seconds divided by the mass of an electron is 9.11 times 10 to the negative 31st kilogram times the speed of light, 2.998 times 10 to the 8th meters per second. But it's not going the full speed of light. It's only going 75% of the speed of light. So what I do is I just add in times 0.75. So that means that that'll take 75% of the speed of light, and it'll calculate that way. So you can add all of that in just one step. So what would that be mathematically? So once again, make sure you do this math in the denominator first, and then plug that into the rest of the equation. So if you know how to use your parentheses on your calculator, you can do that. Otherwise, you can just do it in steps. So 6.626 e negative 34 divided by the product, parentheses, of 9.11 times 10 to the negative 31st times 2.998 times 10 to the 8th times the 0.75, so we can take 75% of that. All right, and my answer is going to be 2 sig figs, because this 75% is a measured value. Even though it's a percentage, it's measured. And so two significant figures would give me an answer of 3.2 times 10 to the negative 12. Now, what would be your units for this answer? Well, here's one way to think about it. This is the easier of the two. Since I plugged in the SI units for Planck's constant, mass, and velocity, it should report out then the SI unit for wavelength, or just length. And what is the SI unit for length? It's the meter. But some students say, well, wait, hold on. How is it that you had joule seconds, kilograms, and meters per second? How does all of that somehow equal a meter? Well, I'm going to show you right now. If you don't want to see, you can just stop the video right here because we're done. We'll see in the next video. But if you want to see how all of that ends up turning out to be just meter, I'm going to show you, because I actually think it's really interesting and actually a very valuable tool. So I'm going to remove all the numbers. Instead, I'm just going to look at the units. We have joule second on the top, and on the bottom we have kilogram and meter per second. So the second, the meter, and the kilogram are all basic SI units. You can't break those down any further. But if you recall, the joule is a derived unit. The joule is actually a Newton times a meter, which even the Newton is a derived unit. So the Newton can be further broken down into a kilogram meter per second squared. So now you can probably start to see a little bit how things start canceling out. First of all, the kilograms will cancel each other out. So let's go ahead and erase those. So then we have this stuff left over. Let's clean up the top. We have a meter per second squared times a meter times a second. So that would convert to, or simplify, to the meters would now be squared because we're multiplying them by each other. This second right here will cancel out one of the seconds right there. And so it would be meters squared over second. And this is going to get divided by meters per second, which was down here. which is the same thing as multiplying by second over meter. The seconds cancel, and that meter will cancel out one of those meters. And that's how you end up getting meters. Like I said, did you have to necessarily know how to do that? Not really, although that trait or that skill is going to be extremely helpful the further along in science you go, especially if you need to take physics. So keep that in mind. All right, we'll see you in the next video to continue on with quantum mechanics.